Alright, to continue talking about graphs of log functions, let's just mention this term here. A common log means that the base is 10. In other words, log of x base 10. It's so common that if you don't write any base, 10 is understood to be the base. And as I mentioned, this was the base that Napier worked in. So all of his logs were this, and people never even thought about using other bases. Later on in mathematics, people realized, oh, I can get use out of thinking of other bases like 7 and 3 and whatever. Okay, so common logs, and you will see this key on a scientific calculator. A log key without any base written there. Now we talk about transformations of graphs quite a bit, so let's take a quick look as to what happens to the log function when you do a transformation. Example 7. Here's the common log function. Y equals log of x. I didn't write a base, so that means the base is 10 automatically. And it just has that familiar curve, familiar to log functions where the base is greater than 1. Now here, again, we want to talk about the common log function, but instead of plain old vanilla x, it's going to be the log of x plus 3. What's going to happen there? Well, every y value that's output here is going to happen 3 steps earlier, right? When y is at when x is at -2, it's going to behave like this function behaves when x is at +1. So we'll have that point, and the whole thing gets shifted over 3 places, 3 units to the left. So this means shift left 3 units. If we look at part B of this example, we have y equals 4 plus the log of x minus 2. Well, here when I added 3, it took me to the left 3. So now I'm going to subtract 2, and as you might expect, that's going to pull me to the right 2 places. So the unadulterated log function went through the x-axis there. Now I'm going to shift right 2 places. So this new function is going to go through there. But that's only taking into account the x minus 2. I also have this 4 being added on. And we know what happens when you add 4 onto a function. It shifts it up 4 places. So the point is not really going to appear there. It's going to be there. That's what happens when I shift 2 to the right and then up 4. So now I have that familiar curve going like that. And it will be asymptotic right here. Asymptotic to the vertical line x equals 2, which it never gets to. Okay, now you do one. Do number 17 on page 340. And we'll see what you figure out. For 17, you have this function. We see that there's a 2 being added on outside of the log expression. So we know the graph is going to get shifted up 2. remember in our last example it got shifted up 4. I'm adding 1 on to the variable which is being put into the log function. So we know that that's a shift to the left of 1. So I take my basic generic log function, which looks like that, and it goes through 1 on the x-axis, shift it over 1 place, so now it becomes asymptotic to the vertical line through x equals -1, and shift it up 2. So instead of going through the x-axis there, we're going to go up 2, and that goes through that point there. And that's how you could do number 17 quickly. Of course, if all else fails, you can graph any function if you can plot enough points. Just pick x values, you maybe use the log key on your calculator, add your 2, and you will eventually graph a few points and figure out, oh, it got shifted over to there. Of course, you can use the Desmos program too, which will take care of everything for you at once and produce a beautiful graph for you. Okay, so that's a few examples involving common logs. The other major type of logs is called natural logarithms. And a natural logarithm means when you have the base e, because as we said in our chapter on exponents, e is really special, very special number. It's so special that when you want to do a log where e is the base, you could write it like that if you felt like it, but the normal way to write it is ln of x, natural log of x. Since e is greater than 1, it has the typical curve like that. Okay, so we will do some work with natural logs also. To do that work, we're going to look at properties of logs. This is on page 335 in your textbook. On page 335 you see the 5 basic properties listed. Oh, and I've already got it out. That saves a little time. For b, a positive number not equal to 1, the log of b to the base b is always equal to 1. And we could prove that easily if we just take log of b to the base b and write its corresponding exponential function. You're going to see that this has to work out to be 1. Similarly, for property number 2 here, if we wrote this as an exponential number, it would say b, exponential expression, it would say b to the power 0 equals 1. The first one just said b to the power 1 equals b. All right, we know all that stuff. Here, if you take the log of b to the power x to the base b, it turns out it's just equal to that power x. It's like the exponent just gets moved to the outside and you can throw away the rest of it. Yeah. B to the power log of x base b is also equal to x. And finally, if you have two algebraic quantities m and n and they're positive, then the log, if m and n are equal, then the log of m to the base b is equal to the log of n to the base b. And it better be, because we already said that log was a function. If this wasn't true, then we would violate the function requirement. We would fail the horizontal line test. Sorry, we'd fail the vertical line test. It would not be a function. Let's look at example 9. We now have enough properties and concepts to simplify some log expressions. in part A, we're thinking about the log base 5 of 5 to the power 10. How can we simplify that? Let's leave these up here. We can refer back to them. Well, what I see is this situation here. I have an exponential quantity that I'm taking the log of, and the base of that exponential quantity is the same as the base of my log expression. So it's a perfect match with property 3, where 5 plays the role of b and 10 plays the role of x. Therefore, this must be equal to 10. That's how I can use property 3. Part B, the log of 4, base 4, what is that equal to? I recognize that. That's property 1, with 4 playing the role of b. And it makes sense if I think about it. 4 to the power 1 equals 4. Right. Can you simplify this? Log of 1 to the base 4 equals what? Well, 4 to this power equals 1. Well, right, the power always has to be 0. So we're using property 2 there, or just reasoning it out from scratch, however you like. Log of 10 to the 7th it's a common log, so this base 10 is the same as the base of the log. So it's one of these. It's property 3. Therefore, I know this just equals that exponent 7. Part E, natural log. The natural log of e cubed. Well, as we said a couple minutes ago, natural log is just a shorthand way of writing log base e. So once we recognize that, we say, oh, it's this situation again, where we're taking the log of an exponential quantity and the base of that exponential quantity matches the base of the log. In other words, e is the base here, e is the base there. Therefore, this just equals the exponent. And finally, part F involves some division. The common log of 1 over 10 cubed. Well, you can quickly simplify this if you just convert 10 cubed, 1 over 10 cubed, that is, to its exponential form, 10 to the minus 3. Then use property 3, say, oh, it's just equal to the exponent. Okay, now you do a couple. On page 340, do number 23 and do number 25.